In this upcoming section, we're going to focus a little bit more on whether a series, an infinite series, converges or diverges by performing a series of tests. We have 7 that we're going to look at, and it will take some time to get used to the prereqs for each test and the parameters and the analyzing of the results. But ultimately, the question is, will this infinite series diverge or will it converge? So for example, we've looked now quite a bit at the geometric series, and we concluded that it converged so long as our common ratio was between -1 and 1. Then when we added x to the mix, we came up with a power series of 1 over 1 minus x, that template series that you've all have memorized by now, and concluded that since x is in the spot of r and it represents our common ratio, that it had to be between -1 and 1 in order for the function to converge. And so for any power series, there's 3 instances in which the possibilities for convergence can be determined based off of whether the radius of convergence is an interval like you see in the geometric series, or does it converge for all real numbers, or maybe it's so bad that it only converges at the center. So for example, in the, and I'll highlight the 3 different conditions that can result, but you have case 1, case 2, and case 3. Case 1 is like a geometric series where if you're looking at the interval, if we think about the center of an interval being like in the problem above there, the interval of convergence being -1 to 1, we would say that the center is at 0. So if the center was anywhere else, we've now are used to calling it x equals a for our Taylor series. The radius would be plus or minus r in either direction. So think of a circle, think of the radius of a circle, and this would be positive r in one direction and negative r in the other direction. So the conclusion is that the series would converge so long as the distance between the center and your x value is less than the common that radius value, that finite radius value. And in this the above case, that radius value is 1. So long as it's less than 1 or greater than -1, we would say that the series converges. So that's if you had a interval convergence that was between 2 finite values. And our conclusion for the geometric series was if it was beyond that, if you had to estimate a function beyond the interval of convergence on either side of plus or minus r, then what we would say is that it's no longer a good approximation, it diverges. So therefore, the distance between x minus a, if that is greater than the radius of convergence, then we would say it wouldn't be a good approximation. So there's going to be discussion of an interval of convergence and a radius of convergence. So just to be clear, if the interval represents the diameter of a circle, the radius is simply just half of that value. So once again, this is going to represent, when we refer to interval of convergence, think of interval of convergence as the entire span of what would physically look like a diameter. And then the radius of convergence is that plus or minus r. We call it r for ratio, also for radius. Okay, and so the next idea is when we explore this next section, we might come across a few where that we get infinity for the radius. So let's think about what that means. If infinity is the radius of my interval of convergence, then on one endpoint you have negative infinity, on another positive infinity. And so it's a good approximation for all values of x. And so we saw a few of those power series as well. And so if r is equal to infinity, we would say it's a good approximation for all real numbers of x. And so I want you guys to think, for example, when we looked at sine of x, and let's say Maclaurin series for sine of x. So think of the Maclaurin series for sine of x, for cosine of x, and for e to the x. And we will be able to show that this is true for those 3 functions in the coming examples. And the worst case scenario is if your polynomial ends up being only a good approximation at the center. And so that's scenario 3 that you see here. It only converges at the center, and everywhere else it's divergent. So basically at one single point, and then everywhere else it's a bad approximation. So for this one, for your notes, let's say that you want to refer to an example of when this happens. Go ahead and write C example number 13. So I put together this packet when I first started to teach Calc BC because I wanted to organize all of the tests for you with some examples of what it would look like. So a few you guys actually already know of, and then there's some that we're going to add to what we thought we knew before, like the limit comparison and the direct comparison tests. And so this video is an introduction to it, as well as to the nth term test. So the nth term test is going to be the very first test that you guys always try. Okay, so you're going to say always try first. Okay, so for the nth term test, what you're going to do is basically take the limit of the nth term. So take limit of nth term. And what we find is that if you get any value aside from 0, your conclusion is that it's divergent. Okay, so it's called the nth term test. It diverges if you get anything besides 0. If, however, you do get 0, your test is going to fail. So test fails if you get 0. So over here, you guys can say anything but 0. Your conclusion is that it diverges. So if it's anything but 0, it diverges. So let's take a look at example number 1. You're given an infinite series because I have summation notation from 1 to infinity. And then this is my nth term, also referred to as my general term if I were to expand it out. And if I take that and also just add a note here that this is your nth term, this is a sub n, referred to as nth term or general term. That's basically the rule that you guys would use to expand out your series if you needed to. So we take a look at that, and the question is determine whether, and I think this spilled over a little bit, determine if this series could be convergent or divergent. So what we're going to do is take the limit as n goes to infinity of the expression that you see for your nth term, and we see that the n over n has a ratio of 1. So the answer to that limit question, so we view that as a limit question, is 1. So I like to think of it as if I'm adding terms to a series that is that's not approaching 0 or not really close to 0, then what happens to the series is the partial sums are just going to start getting larger and larger, so therefore the series diverges. So our conclusion is, since it does not equal 0, your conclusion is it diverges, and that is a notation simply for therefore it diverges. On example 2, if we do the same thing, we take the limit as n goes to infinity of 4n squared minus n cubed all over 2n cubed plus n squared. We might first think, okay, this is 0 because there's a bigger bottom, but we want to make sure that we're looking at the highest power on top and bottom, which is those two. And we conclude that as I go out to infinity, my limit is the ratio of the coefficients, and that is -1/2. Again, that comes from the -1 here and the 2 here of the highest and leading term of the top and the bottom. And then since -1/2 is not equal to 0, since -1/2 is not equal to 0, therefore your series diverges. And sometimes they'll ask you, by what test do you know that? And you would say by the nth term test.